Alright, so here's our chapter 17 homework. And so we're going to start with question number 1. My name is James Lewis. So we start out with our givens. We have our flywheel, which there isn't very much to do in our free body diagram, but we've got a velocity of 300 RPM. We've got work, 1,800 foot-pounds of work on it, and we have a final speed of 270 RPM. I mean, obviously all of that is just happening all around the perimeter of the flywheel. Again, that's why I said there's really not much to do here in this free body diagram. Anyway, we're supposed to find the required inertia, and B, we're supposed to find the revolutions between each punch. That is with our starting value of 270 RPM, waiting until it gets up to 300 RPM, and that's with a moment of 25 foot-pounds. Basically acting on it. So first one, we start with our equation. We have our initial kinetic energy plus our work equals our final kinetic energy, and this is and we're using this, and we're not putting any potential energy or potential elastic energy because there are no springs or gravity involved in this. So we have our 1/2 inertia angular velocity squared plus our work equals our 1/2 inertia W2 squared. After reorganizing everything so we can get inertia just on one side, we end up with 2 times the work over the final angular velocity squared minus the initial angular velocity squared. That is equal to 218. And anyway, yeah, so after inputting our numbers, we get our inertia equals negative 0.12053. And at first I was wondering why it was negative, but it's because the punch is doing work, so it's losing work. It's like losing work, and the work is not done on it. The work is actually negative, so our inertia would actually be 0.12. So then with part B, we have the same equation. Kinetic energy plus work equals our final kinetic energy. And with this one, our work is our moment. Our work is our moment times the distance, which we're going to put as theta. And theta is just going to be represented as revs, because we don't have to convert to rads per second. Yeah, we don't have to convert to rads per second or anything, because we're just going to keep everything as RPM. And then we reorganize everything so that theta is on one side, like our distance, which, let's see here. Yeah, I did that right. So our revolutions equals the inertia times the kinetic energy, the final kinetic energy squared minus the initial kinetic energy squared over 2 times the moment. After inputting all of those numbers, we get the revs is equal to 615,600. So there's 615,600 revolutions in between punches, just so that we can bring the revolutions back up to 300, which is pretty understandable. It's going to take a whole bunch of revolutions because we're only having a moment of 25 foot-pounds on there, which is a really small input. Question number 2. We have our bar, which is resting in a horizontal position, and we have a length, we have a weight, and we have a velocity, which is dependent on the weight, so we're just going to stick our velocity here in the middle of it, and our angular velocity on the outside, but wherever. And then this is our fixed point, which is our origin. I guess I should just draw O for origin. There we go. So part A is to find the angular velocity at the vertical position. Here's our O again, our origin. We have our length, our weight, which is pointing downwards, and our angular velocity. So this one, there's no work done on it, but there is a gravitational potential energy. So we're going to set up our equation, our initial kinetic energy plus our initial um, our initial um, our initial gravitational potential energy equals our final kinetic energy plus our final potential energy. And since we're setting our final potential energy as here, and we're gonna call the height 0 here. Yeah, we're gonna call a height 0 here, and there's no initial speed here, so initial speed is gonna be 0, and our potential energy is going to be 0, which is out here, but we didn't put it because it's 0. And so we have our potential energy, which is mgh, equal to 1/2 times inertia times angular velocity squared plus 1/2 mass times velocity squared. We want to get everything in terms of these parameters: our length, our weight, and let's see, our weight, our length, and gravity, just because those are the only inputs that we were given. Those are the only inputs that we were given, our length and our weight. So we have our weight is equal to mass times gravity. Our inertia, because it is a shaft, a rod, pivoting on one end, which is 1/3 mass times length. Let's see, mass times length. Our height is equal to length over L/2, and our velocity is equal to L/2W, and velocity is normally equal to the radius times the angular velocity, but because we're looking at the mass in the middle of the bar, it's going to be L/2. So we input all of our numbers here, and that's just coming from this equation. For example, we put our mass times gravity, we substitute that with the weight because we know the weight, and then after doing all of our organization here, we put in our with all of that, we put in our equations. All right, cool. Well, and anyway, I ended up figuring out, or just noticing, that I didn't put a squared up here, so the inertia is equal to 1/3 ml squared, which, by the way, would change over 3 ml squared. Anyway, I think I did something wrong there, but anyway, we ended up plugging in all our numbers, and then we got everything in regards to the angular velocity. And then with this equation, we have our weight, or we have a given weight, a given length, and a assumed gravity. Put all those numbers, and then we get 28.78 radians per second is equal to our angular velocity. And then for question 4, went ahead and passed by question 3, because we're going to come back to that later. Our free body diagram, we have our wheel, which this is the center of our wheel, and here's the lug nut on the outside of that. We have a moment designated as 1 and a length of 1 equals 50 millimeters. We have a time that our impulse is happening is 10 seconds. The mass of our wheel is 19 kilograms. The initial angular velocity is 0. The final angular velocity is unknown. That's what we're trying to find. And our radius of gyration is 250 millimeters. So first we need to find out that first moment that's out here. That's out here because the moment 1 is acting on the center point, and our moment 2 is acting on this lug nut, which is right here. So we have the length between the moments of 460 millimeters, and that's basically the same as just going, your length is 460 times the force. It's just definition of the moment. And so before we calculate the moment here, we're going to take the center of the wheel that's here at G1, the lug nut that's at G2, and the force that's being applied at this point out here. We're going to shift this point out so that we can extend it, because a moment happens in 360 degrees, so it doesn't matter where we stick the moment arm. So we're just going to stick it out, coming out this far, and it's going to make it a little bit easier for the math and just turn everything into one problem. So we have our length equals 510 millimeters. Our moment is equal to the force times the distance, like the length of the moment arm, which is 100 newtons times 0.510 meters, and we're going to convert that over to meters because we want to do meters instead of millimeters. Our moment is equal to 51 newton meters. Then we'll take our impulse equation, kinetic energy plus our impulse equals our final kinetic energy, 1 over 2 times the inertia times angular velocity, the initial angular velocity squared, plus the moment times time, which is our impulse, equals 1 over 2 times the inertia times angular velocity, the final angular velocity squared. We are trying to find the final angular velocity, which is 2, so we just put the final angular velocity. This one, the initial speed is 0, so we can just zero all of that out, which equals our moment times time equals 1 over 2 impulse times angular velocity final squared. And then after reorganizing this so that we can get the angular velocity on the outside, we have 2 times the moment times time over the impulse equals final angular velocity. Since we aren't given an impulse, we have to figure that out from the radius of gyration, which is our mass times radius of gyration squared. K equals square root of I over m. And then we have our final angular velocity equals the square root of 2 times the moment times time divided by the moment, or divided by the mass times the radius of gyration squared. Plug in all of our numbers, and our final angular velocity is 0.46340 meters per second.